Good afternoon, everyone. Thank you so much for joining us. My name is Katie from the NOAA Central Library, and we are very happy to be co-hosting this seminar in the NOAA Innovators Series today with the Technology Partnerships Office. As you are an attendee, you are muted throughout this entire presentation. If you have questions or comments, please place them in the question or the chat panel. Either one will work. If you are having any kind of technical difficulties, like you can't hear me or you can't see the slides on the screen, please let us know, or try logging off GoToWebinar and logging back in. That solves most problems. We are recording today's seminar, and if you place a question or would like to speak with the presenter later, we will be recording your questions and your information to pass on to the speaker. And with that, I'm going to turn it over to Tiffany House to introduce our speaker.
Thank you, Katie. Hello and welcome, everyone. Thank you for joining us. My name is Tiffany House. I am the Commercialization Specialist of the NOAA Small Business Innovation Research Program. The NOAA Innovator Series features highly innovative products and services inside and outside of NOAA. NOAA employees and SBIR Principal Investigators who do work relevant to NOAA's mission present their research to other NOAA employees, external partners, federal agencies, and researchers. The SBIR program, also known as America's Seed Fund, allows U.S.-owned and operated small businesses to engage in federal research and development that has a strong potential for commercialization. Our speaker, Dr. Ben Cameron, will provide an overview of novel drones that combine the long range and endurance of fixed wing platforms with the convenience and small operational footprint afforded by vertical takeoff and landing. The technology is available for Phase 3, and Phase 3 is non-SBIR follow-on funding and is oriented towards commercialization of the SBIR research or technology. And once an agency determines if the SBIR company is available, capable, and willing to perform the work, NOAA or any other federal agencies that participate in the SBIR program can award a Phase 3 through a sole source procurement. Dr. Cameron has served as the Principal Investigator for multiple NOAA SBIR projects focused on drone platform development. At Creare, Dr. Cameron leads the Unmanned Aircraft Systems Research Group and oversees development of complete drone systems and airborne sensor packages for specialized scientific missions. So without further ado, I'd like to turn it over to our speaker today, Dr. Ben Cameron.
Great, thank you, Tiffany and Katie, for that introduction. So just to reiterate, my name is Ben Cameron. I am from Creare LLC in Hanover, New Hampshire. And in addition to leading the drone development group, I am also program director for a variety of projects. And myself, I'm also a technical R&D engineer. As Tiffany mentioned, this seminar will be providing an overview of these novel drone platforms that we've been working on that combine fixed wing platform capabilities with vertical takeoff and landing capabilities. These platforms offer longer flight endurance than comparable platforms on the market today and are useful for a wide range of Earth and observation missions, from potentially long-term unattended atmospheric profiling to remote missions with heavy payloads and requiring multi-day flight endurance. There are also many other possible applications for this type of platform, and I'll briefly describe those throughout the presentation. So the systems that I'm presenting today specifically, I would consider them scalable, and that's why I've shown these two platforms that you see on the slide here. The small platform, which you can see on the right two images, has a takeoff mass of about 500 grams or roughly 1 pound. And it is what I call a VTOL quad ring wing because of the shape of the wing. The largest platform that we have developed to date is a 25 kilogram takeoff mass, which is 55 pounds. It's shown in the two pictures on the left. Even larger systems are possible, but these fall outside Part 107 FAA regulations and require additional flight clearances, so that's why we've limited so far to 55 pounds. Both of these drone systems were conceptualized and prototyped through NOAA SBIR programs. They're similar to each other in concept and control, but have been optimized for particular application. So for example, both systems take off and land vertically within a very small operational footprint and then transition to horizontal flight to reduce flight power and increase endurance. And you can see that through the sequences of images here, both for this large drone on the left and also for some snapshots within the same video frame on the right. The large system is designed for shipboard operations, where takeoff area may be small, like only 3 by 3 meters or so, and it can carry a 15 to 20 pound scientific payload. The small system on the right was designed to autonomously profile the atmosphere up to approximately 25,000 feet and then descend under low power flight back to a base station where it then must land onto a very small landing pad. And so that's the kind of the common theme among these classes, this class of drones. See if I can advance this slide here. Here we go. So just a brief overview of the talk. I'll provide a brief introduction to Creare, explain the motivation for why we wanted to develop these VTOL drones in the first place, describe some of the concepts of operation in a little bit more detail with some graphics, talk about flight performance capabilities and also comparisons to other drone configurations that are commercially available and on the market today. And finally, I will discuss very briefly just the current status of our programs and potential future applications or future applications for these types of systems. So a little bit about Creare. Creare, our company name, means to create. We have a staff of more than 140 people with about 70 engineers and more than 40 technical staff spanning a pretty broad range of disciplines. And that's what makes this a really great place for developing drone platforms, because it's a very multidisciplinary type of technology. So our core technology areas, again, we're pretty broad, but I describe them as fluid thermal, cryogenic systems, biomedical systems, sensors and controls, and obviously some of these are applicable to drones and some are not so much. Advanced manufacturing, power systems, electronics, software development, and obviously, of course, drone platforms. We leverage a lot of these different technologies to help aid in the development of our drone systems. And we also provide technology services such as prototyping, which we often use to build drone hardware, and product and process development, which comes potentially later on when these technologies start to mature. Our facilities include about 60,000 square feet of office, lab, and fabrication shops in Hanover, New Hampshire, and we also have another 20,000 square foot facility a few miles down the road in Lebanon, New Hampshire. We maintain dedicated electronics labs for design and testing of custom boards, which can be used to support drone avionics and sensor packages. We have a range of facilities that support performance testing of drones. There's some examples down on the lower 4 pictures. A couple of lab grade test stands. The one in the middle with a big frame around it was capable of testing propellers up to about 4 feet in diameter. And we have that large wind tunnel for aerodynamic testing of drones. Creare itself was founded in 1961 and has a number of successful spin-off companies over the years, including a computational fluid dynamics package called Fluent. And we use that package often to model the aerodynamic performance of our drones. We are primarily an R&D company, and we commercialize our technologies through multiple channels, including spin-off companies, as I mentioned. And these companies that have technologies initially developed at Creare currently employ more than 2,300 people and generate revenues around $500 million per year. And so you may hear me say this many times through the presentation, is since we're generally focused on R&D, we really are looking for industry commercialization partners to transition these technologies into the field. We do have some examples of what we call high value products, where we actually produce something that's used And a couple examples there just to highlight that are, for example, cryocoolers. We installed one on the Hubble Space Telescope, and we also design and fabricate miniature vacuum pumps which go into space for space missions for NASA. And we also happen to be currently working on a program with NASA JPL to develop a drone design for exploration of Saturn's moon Titan. And we are using the ring wing concept that I showed on the prior page. All other technologies commercialized through Creare include machine tools, non-contact inspection tools, and novel fasteners that were used on the space shuttle and modern commercial aircraft. And as I said, our drone development programs benefit greatly from all of these different technologies at Creare. There's a lot of overlapping capabilities related to sensors, imaging, and fabrication. Okay, so on to a bit about the motivation for these so-called quad planes, which is a kind of a general term I use to describe these types of drones. So a few years ago, there were some SBIR calls where the NOAA and the Earth observation community had identified drones as a really big opportunity to improve access to Earth and atmospheric data. The drones will promise to provide data in remote areas and over larger geographic regions than possible with traditional observation methods, and then also at a much lower cost to piloted aircraft. Currently available drones that are commercially available are not necessarily well designed to meet the requirements for many of the NOAA applications, which may require simple launch and recovery operations combined with the long endurance, long range and low cost, and sometimes unattended operations. So multi-rotor drones such as the quadcopter, which I'm sure we're all familiar with, are used in many measurement and monitoring applications, but they have limited endurance and payload capabilities because they're flying in hovering flight. Existing fixed-wing systems, more like traditionally piloted aircraft, offer improved endurance and payload capabilities, but are difficult generally to launch and recover. In particular for shipboard missions, which is very common for NOAA research ships to want to deploy drones. If there's a somewhat larger fixed-wing drone, they often require support hardware and high-risk recovery tactics, such as catapult launch and recovery by catching the aircraft in a net or wingtip mounted arrestor hook. So those things make operation logistics difficult. And so we look to develop a system that can improve upon those capabilities and make the systems easier to operate, especially from confined spaces and lower cost. So here, just very briefly, Creare's quad planes in general combine the best of both the VTOL of multi-rotor systems and fixed-wing aircraft. That is, the fixed-wing capability improves endurance compared to the multi-rotor systems, and the vertical takeoff and landing capability reduces risk and complexity of launch and recovery. Okay, so I will use this quad biplane to describe the general characteristics of this class of aircraft, and much of what I say will also apply to the ring wing version. So this quad biplane was originally developed, as I said, for a NOAA application, which required long endurance platform, capable of deploying from ships, launching and recovering from ships, and carrying a 15-pound aerosol sensor. The basic concept of operation is shown in that graphic on the right. And it shows the aircraft gaining quite a bit of altitude during takeoff, but you'll see in a video a little bit later on that it actually transitions at a pretty constant altitude, and you can kind of see that here with these snapshots of images here. Since the initial application with NOAA, we've also been funded to develop a design specific for a ship deployed Navy application and we've investigated applications for pickup and delivery of medical supplies in the field, and also for magnetic anomaly mapping for magnetic navigation. And all those applications had some things in common. It was either launching and recovering from constrained areas, or simplifying the launch and recovery efforts. I think those applications, a lot of those applications really benefit from those capabilities. So in general, these quad planes, as I say, are fundamentally similar to multi-rotor drones in control. They take off vertically with 4 counter-rotating propellers oriented facing up for takeoff and landing. And also a number of aerodynamic benefits from this biplane configuration make the transition from hovering flight to horizontal cruise flight very fast and stable. The system, as I said, is able to transition seamlessly without any really change in altitude, which is a really nice feature. The basic quadcopter configuration that you see here, especially you can see close up on the right image, provides an ideal geometry to create a stable base for landing. It's got 4 nice legs to land on, and also functions as a scaffold for the wings and the central fuselage. And it makes the system very modular and adaptable to different types of missions, and allows for quick reconfiguration of the aircraft to meet different mission requirements without necessarily needing multiple mission-specific aircraft. So for example, wings could be changed out, the wing size could be changed to enable slow, long endurance flight, or they could be reduced in size to enable fast, high-speed flight. Or you could trade heavy versus light payloads. There's a lot of trades that can be made there. We also have the option with that central fuselage to use a fuel-based power plant, which would increase range and endurance, or an all-electric system, which could be used to simplify operational logistics and reduce maintenance. And I have some examples to show in some bar charts in a couple of slides about the comparison performance of those different types of systems. In addition to electric versus fuel-based, I just wanted to highlight a couple of alternative large fixed-wing vertical takeoff and landing platforms. The quad biplane configuration that we're developing, it demonstrates many desirable advantages over these competing systems. For example, the quad plane has very high power on board needed for vertical takeoff and landing, and that enables high sustained dash speed in horizontal flight. So if that's one of your mission requirements where you want to fly very quickly to a location, do some sort of sensing, surveillance, investigation there, and then fly back quickly, that's a capability that this quad plane system has. The quadcopter configuration on the quad plane also results in very agile flight because it's a very responsive control system. It's in contrast to a tail sitter, which is shown in the top figure, which utilizes potentially only 1 or 2 propellers in vertical flight. And this agility using the quadcopter configuration is particularly important for shipboard operations or operations just anywhere where there's turbulent air because it's very highly controllable. Also, the biplane configuration, when we're operating in a constrained area, has reduced wing loading. So for example, if you're limited in wingspan, having a biplane configuration can actually improve your system performance by reducing drag and increasing overall capabilities for range and endurance. That statement generally applies for lower speed flight, somewhere in the range of 50 knots or so. Once you start to get up to higher speeds, then the different wing configuration may be more advantageous. But as I mentioned, this system is very configurable and can be suited to those different types of requirements for speed. In addition, the penalty for having a biplane configuration at those speeds, even 100 to 150 knots, is not really that significant on the order of percentage points, and so the advantages may outweigh some of the decreases in performance you might get with a biplane at those higher speeds. All right, so this slide shows a performance comparison of the quad biplane and those other VTOL fixed-wing aircraft that I showed on the previous slide. The plot shows what I call the hybrid quadrotor, which is a fuel-based power plant. And it's essentially, it's the bottom figure on this prior slide here. And it's essentially a fixed-wing aircraft with a quadcopter built into the frame. And then the fixed-wing tail sitter with a single vertical lift and cruise propeller. The comparisons are made for 2 different payloads. On the left here, we have a 15-pound payload, and it's compared to the hybrid quadrotor. So the blue bar is the Creare system, and the green bar is the hybrid quadrotor. On the right is a smaller electro-optical infrared sensor package weighing only a few pounds, and the comparison is made between the quad biplane and that tail sitter. So you can see that for the heavier payload, the quad biplane can sustain a flight endurance of more than 20 hours with a fuel-based system. And for the smaller package, we see flight endurance in the range of 40 to 50 hours. And it's approximately a factor of 2 better than the other leading hybrid quad rotor on the market today for the heavy payload. And it's on the order of approximately 20 hours more on the smaller package. So for completeness, I've also included the endurance of Creare's all-electric quad biplane. So obviously, if you want to reduce maintenance, you don't want a fuel system, you want all-electric, you can still produce a flight endurance of approximately 5 hours with a 15-pound payload, or approximately 10 hours with a smaller EO/IR sensor. All right, I have a short video I think I mentioned earlier that I want to show. If we have any problems with internet bandwidth today, I've put a link at the bottom and posted it to YouTube, so you can go watch that later if you like. I like to show this video in particular because it's the maiden horizontal flight of our first all-electric prototype. We had previously performed a number of vertical flights to tune the system and to check responsiveness and stability in hover. But this literally was the very first horizontal flight. So I hit play here in just a second. You're going to see the aircraft take off vertically and hover like a quadcopter. Then the aircraft is going to transition over to horizontal flight without losing any altitude. So this first flight, the drone flew in the horizontal orientation for really only about 10 seconds at a ground speed of about 20 to 22 knots. This equates to a distance of about 300 to 400 feet, but it proved the feasibility of our design and provided critical flight performance data. And with that, we were able to get a follow-on phase 2. And during that phase 2, we built the next generation version of the system and completed some additional flight testing, and also worked with an industry partner to integrate an autopilot system with a control platform. Okay, so a very closely related variant, which I showed you before, is this quad ring wing. It was initially developed under a NOAA SBIR effort. Even prior to that, we had conceptualized this idea for an Air Force weather sensing application. The system utilizes the same control algorithms, but instead of a biplane, it uses an annular wing. This ring wing geometry was chosen specifically for this application due to its symmetry and some of the sensing requirements we had, where it would sense meteorological data. So on the picture on the right, you can see a drone and a base station, which were designed to perform unattended autonomous atmospheric profiling similar to balloon soundings, except this is a much lower cost system, something like a factor of 10 times lower than balloon soundings. Plus, it is able to provide more data. So for example, at balloon sounding might be launched a couple of times a day. This system could potentially go up once an hour and collect a lot more data. So the drone launches in this concept from a base station, measures the meteorological data or any other small sensing data that you want to see up to about 25,000 feet. It then returns to the base station for landing and recharging and data processing under low power horizontal flight. As you can see on the image on the left, we performed a number of low altitude transition flights and also soundings to demonstrate performance of sensors. This type of system, you could easily imagine a network of these unattended stations that could not only be used for atmospheric sounding, but other types of on-demand applications like monitoring extreme weather events, deployment of imaging sensors during natural disasters, emergency communication networks, and I'm sure countless others. Okay, I think that's all I have on that slide. So here's a list of potential applications for these types of drones. And it's, as you can see, very numerous. And this is by no means all inclusive. And some of them I've already mentioned, but I wanted to just highlight a few other ones. So if there's anyone out there that is listening that doesn't necessarily have an application for Earth observation or atmospheric sensing, that can see some of the other potential benefits to these quad plane platforms. So transport of medical supplies and equipment to remote or inaccessible locations is something we've looked at for the Army. Obviously, search and rescue missions, if you want someone to easily deploy some drone off the back of their truck, they take it out, launch it like a quadcopter, but instead of flying around for 20 minutes, it could fly around for a couple of hours. With larger systems, you can imagine personnel evacuation, where it may fly in, pick up somebody who's potentially wounded in the battlefield and bring them back to a safer location. We also had a program with the Navy that was also an SBIR effort with a similar concept for measurement of a marine boundary layer for electromagnetic wave propagation. And that information is used, that system, like the profiling drone I showed on the previous slide, also profiled the atmosphere, and it measured data to correct radar propagation models. So I think I've mentioned most of the other ones in here, but in general, just to kind of conclude these ideas about applications, essentially any land or ship-based operation that requires long-range and endurance, simple launch and recovery logistics would benefit from a system like this. And as far as end users are concerned, I mean, I think this is also quite broad, but in general, there's many DoD applications that we've already looked at. You know, within NOAA and National Weather Service, clearly you've seen some examples here already. USGS is another potential end user for something like this for monitoring forests or wildlife. FEMA for natural disasters. DARPA, we've talked to about a number of applications that even including shipboard launch applications are kind of scientific research programs. So in general, research scientists might have a need for this for any kind of sensing that's remote, long range, and can be done from the air. And then soldiers and first responders can use this for, you know, survey, surveillance, investigations that are beyond line of sight. And as far as industry is concerned, I just listed a few things here. You know, aerial surveillance companies in general could use these types of platforms. It could be for crops, for agriculture. Utility companies and civil engineering firms might use this for remote infrastructure inspection. Imagine inspecting utility lines with a multi-rotor drone is much more difficult than something that could fly slowly but for a very long period of time. And also micro weather prediction companies that are providing very localized weather forecasts to help companies that are impacted by weather events make logistics decisions and actually reduce their operational costs. All right, so just to kind of wrap up here, I want to give everyone an idea of the status and future development of the program. So as you're thinking about potential applications and any interest that you might have here in these platforms, you'll understand where we're at. So far, we've demonstrated the feasibility and flight performance of these systems through analysis, prototype testing under the SBIR funded efforts. We're now working to find follow-on funding, potentially through SBIR Phase 2 or Phase 3 programs, depending on technology and maturity for a specific application. And we're always interested to hear about your own applications that might benefit from these platforms. And again, just to reiterate, since we are largely focused on R&D, we look to industry to commercialize, and we already have some industry partners. But if there's anybody else out there that has interest in these technologies and would like to discuss how it might be used in their drone business, we're certainly open to discuss that as well. And on the last two slides, I have included my contact information here, which I'll come back to this so that it'll be up on the screen for you. But I would also like to thank NOAA for hosting this webinar event and also for their support of our SBIR programs. And with that, I think we can open up the discussion to questions.
Thanks so much, Ben. This was very enlightening, and we do have a ton of questions.
All right.
So, kick that off with a question we got a few minutes ago. How long is a flight of the Ring drone to 25,000 feet and back?
That's a good question. My recollection, it's been a while since I've looked at these numbers, but it's somewhere in the range of like 30 to 60 minutes or something like that.
Great, thank you. And that would be from launch, correct?
Yeah, from launch to landing. Yep.
Thank you. Is the Air Force weather community using this capability yet?
They are not, and we looked at that application, and a while back, and this is probably 5 or 6 years ago now. I think the Air Force had a couple SBIR programs out about that, but it wasn't something that we were participating in at the time. But if there's someone there asking that question that is interested to talk about that application, I would like to do that.
Great. Our next question. What kind of FAA approvals are required for the prototypes? And what about FAA clearance or flight plans at time of test flights?
Right. So that's a really good question, and that's something that everybody has to address. So for these initial prototype flights, we all were flying under Part 107, which means below 400 feet and line of sight. So for further developing the technologies and deploying them into the field, there's a number of, and I'll try not to get too detailed here, but there's a number of approaches. There's a lot of, there are first UAS test sites that have capabilities to fly at very high altitudes, maybe not 25,000 feet, but 18,000 feet, the base of the Class A airspace. And then there's other restricted flight areas where you can get permission to fly outside the normal FAA requirements. And so there's ways to kind of incrementally step up into further deploying these. And what we found with the FAA is once you have a use case and once you've demonstrated capability and some safety standards and some safety records, you're able to further progress in getting approvals to operate outside of the Part 107 requirements.
Great, thank you. Our next question. Are your industry partners American only?
They are, yep.
Great, thank you. Okay, we have a question from Tiffany, so I'm going to let her ask that.
Thank you, Katie, and thank you, Ben, for presenting again. It was good to get an update. I had a question. I wanted to hear more of the story. So do you have any stories on some of the successes or challenges that you faced with this technology?
Let me think here. I mean, amazingly, none of those systems have actually, we've had any even hard landings with them. They've all been successful in the flight testing, and that includes that first, you saw the first horizontal flight test. So it's actually been pretty uneventful in terms of notable failures or anything that we had to recover from. It really has kind of progressed pretty smoothly. So I'm not sure if I can point to anything in particular that's noteworthy. I just think in general, we went through this process of coming up with a design, an aerodynamics design, evaluating it through testing using some of those test stands like the thrust test stand that we had, doing high fidelity aerodynamic or computational fluid dynamics analysis on it. And through doing all of that, and then incrementally approaching that horizontal flight test, or the first horizontal flight test that we did, through starting with vertical flight tests and analyzing data and progressing in a very slow, methodical way, we were just able to make it work on the first time. So yeah, I can think maybe of one thing is the wind tunnel that I mentioned earlier in the earlier slide that we have, it's about a 2-foot cross-section wind tunnel. We needed a bigger facility, so we went to one of the partners that we have for testing larger components, and actually took our 4-foot propeller test stand and put it in their wind tunnel and tested it there. Among that, we also did some larger scale prototypes, testing the aerodynamic lift and drag on those, and that was actually a pretty interesting event. It took a lot of planning, and it was pretty valuable.
Thank you, Ben. And I could not tell from what you presented today. Where are you with the technology? Is it commercially available yet?
It is not. It's all come out of SBIR phase 1 and 2s. And so at this point, what we have is kind of what you might call a working prototype. So there's definitely some development that needs to go on to mature the technology. We still do have that ongoing NASA program where we're working to improve the flight controls of the system, and that's specific to the ring wing platform. And it is becoming more and more integrated into a commercially available autopilot system. So eventually, especially after the end of that phase 2 NASA program, we're going to be much closer in terms of the control system. And as far as the hardware is concerned, you know, that would also require some additional development work to just demonstrate reliability more thoroughly, and to, you know, do things like reduce the cost of manufacturing and those kinds of things.
Okay, that makes sense. All right, I'm going to turn it back over to Katie in case she had any more questions from the audience.
Thanks, Tiffany. We do have a number of questions still, and most of them are regarding wind speed and weight, capacity, etc. So the first question is, what is the max wind speed that each drone can safely operate in?
So we don't have a strict upper limit on that. Right now, I think we've said that quad biplane operational upper limit is somewhere in the vicinity of about 20 knots. The smaller system, I think, could potentially operate higher than that because it's a little bit more agile than the large wings. Yeah, so that's probably the best information I have at the moment.
Okay, and since high atmospheric profiling, the winds are, you know, commonly quite high, how would you mitigate the issues of collecting measurements and still be able to return and recover the platform?
Yeah, that's a really good question. So our systems, both of those systems I showed, are relatively slow flyers. The quad biplane for the NOAA application was actually designed to fly slower because it was an aerosol sensor platform, and that required, or it desired, to have lower flight speeds, so like 30 knots or something. For one of the other applications, we developed a system that would fly up to 150 knots. And when I say developed, we developed it. It was a design. It was a paper study. So how do we mitigate, answering that question directly, how do we get back to the base station, basically? So what we did during the NOAA project for that atmospheric profiling drone is we developed what we called a safe return trajectory. So as we would fly up, we're measuring winds, and we would constantly be calculating the energy required to get back to the base station. And we'd also have, well, what should I say? We also tested it relative to the average winds aloft at, I believe, the Gray Main balloon sounding station, because it was some of the most adverse conditions that you could get. And so through combination of a good algorithm development and power management during the flight, we were able to demonstrate that we could fly up to those altitudes, even in very severe wind conditions, winds aloft, and then also return to the base station.
Great. Following up on that, how do both vehicles perform in that turbulence?
Yeah, they're all, you know, as I say, they're kind of based on a pretty agile multi-rotor control system, and so that controllability makes the platforms very stable. So they're not really impacted significantly by atmospheric turbulence in terms of their ability to maintain stable flight.
Okay, thank you. What is the max weight that either drone can handle?
So as designed, as I said, with a quad biplane, we limited it to 55 pounds just because of the FAA Part 107 regulations. We did also look at an application, where we were thinking of something on the order of hundreds of pounds, like 500 pounds. And again, that was a paper study. The payload capability for the 55-pound system generally was initially designed for 15 pounds. But we looked at one application where we increased the payload up to above 20 pounds, so almost half of the system weight. And I would say that, it's really just a trade-off between, you have a certain amount of battery or a certain amount of fuel on board, and it's really just a trade-off of how much endurance you want versus how much payload you want to carry. So for the smaller system, where our goal was actually to make that as small as possible. We had a suite of atmospheric sensors on board, and we were trying to minimize that sensor package, trying to minimize the avionics and make it as small as possible. And to date it was the last iteration was something around 500 grams or so.
Great, thank you. Our next question, can these systems transition to in-flight hovering to loiter over a target, such as marine mammals?
Absolutely. Yeah, at any point they can transition back and forth. And since that transition is pretty stable and doesn't require really any altitude, it's easy to do that. Yep.
Great, thank you. Have you been measuring noise levels that are important when using the platform for wildlife observation?
So thus far, the answer to that question is no. Thus far we've been primarily or only testing all electric systems, and those are pretty quiet. They're basically as loud as the electric motors and propellers. And I would say the larger systems in general seem to be a bit quieter than some of the higher frequency noise that you might hear from some of the smaller multi-rotors, where the rotational frequencies are much higher and there's a lot more shear at the propellers.
Great, thank you. Our next question, did you test these on ship deployments? Does the deployment require a stationary ship, or can the ship be underway? And can the drone be landed back on the deck of an underway ship?
Yeah, we have not tested on a ship, but we have tested on moving platforms. One of our drone systems was tested on a moving platform. We basically had a trailer that we towed behind the truck, and that was the main objective. And one of the things that we did as part of that SBIR program is we looked at basically ways to very accurately localize the position of the drone relative to the ship deck, even without GPS. So GPS could get it in close, and then there's some other simple guidance system like an optical recognition system that could guide it in to, for example, an infrared beacon or some other optical approach.
Great, thank you. How long does it take to fully recharge the battery on the quad ring following a full profile mission?
In general, they're lithium polymer batteries or lithium ion batteries, and in general, the charge rates for those are recommended for about an hour to increase life or maintain maximum life. You can charge some of those as fast as about 10 or 12 minutes. And we've done that before. The trade-off is that you don't get quite as many charge cycles out of them.
Great, thank you. Do the drones fly in precipitation, and what types of precipitation are hazardous to the drones?
So conceptually, yes, they can fly in precipitation. We have not done that because we've been only doing prototype testing. I would say that in general, what would be most hazardous in terms of precipitation would be icing conditions. And we to date have not really looked at or addressed that. We're a little bit too early in the technology development to have gone over that yet.
Okay, thank you. Next, what is your best estimate for the cost of the system?
I'm not sure if I have a really good number for that, but it's going to depend a lot on the capabilities. Certainly an all-electric system is going to be lower cost. It's not going to be $1 million. It's going to be, if I had to put a number on $100,000 or less, depending on the capabilities. And if it's that's maybe for a bigger system. And they could get down a lot less expensive than that as they start to be mass produced and start to get more cost competitive with some of the other systems on the market today. The smaller platform is, it's hundreds of dollars worth of hardware, so it's not going to be very expensive at all.
Great, thank you, Ben. We are running up to time, so I'm going to try and grab one more question. Can the ring wing drone fly greater than 25,000 feet?
I think in theory it could, but what really limits its altitude capabilities is how much energy is stored on board. So, if it was deployed from a higher altitude and it was designed to fly at above 25,000 feet, I think it could. And And if there was an application that required some other altitude, we could look at that and, trade off payload for additional battery capacity. So I think the answer there is conceptually yes, but the current system is really just limited by how much energy it has on board to fly up to altitude.
Thank you so much, Ben. Okay, we want to honor everyone's time, so we are ending this as scheduled at 12:45. Thank you everyone for asking questions. If we did not get to your questions, and there are several we did not get to, I will pass those on to Ben after the seminar and he can tag up with you offline. With that, we did record this. It'll be put up on the library's YouTube channel. And if you do want the slides, please reach out to us at library.seminars@noaa.gov. Thank you, everyone, and I hope you have a wonderful rest of your day.